Hello everybody, I am Abel Gomez. Welcome to my presentation here in the Practice and Innovation track of Models 2020. I'm going to present this work, a model-based approach for developing event-driven architectures with AsyncAPI. This is a joint work between Universitat Oberta de Catalunya and Ikerlan, and I have developed this work together with Markel Iglesias, Aitor Urbieta, and Jordi Cabot. This presentation is going to be mostly practical. At least I'm going to show some excerpts of code, but anyway, let me explain you first a bit of the background of this work. Basically, as we already know, there are more and more devices whose hardware and software parts are inherently intertwined. These are the so-called cyber-physical systems. These cyber-physical systems are able to communicate to each other without requiring any kind of human interaction. But these cyber-physical systems are normally quite limited in terms of resources. So most of the data they acquire must be sent over the internet to other services, for example, to the cloud. So given these limitations, we need to create very scalable architectures. And one of the most used paradigms to build these architectures is the so-called publish-subscribe paradigm. In this publish-subscribe paradigm, what we find is that devices that want to receive some kind of information subscribe to a given topic. And when a device that wants to publish or is able to publish this information or to provide this information publishes it, and this information flows from the publisher to the subscriber through the broker, which is an element that is in charge of managing all this communication. And this paradigm is especially useful in the so-called Industrial IoT or IIoT. And here is where our partner Ikerlan comes into play. Ikerlan is a research, it's a research center that belongs to one of the largest industrial groups in Spain, that is Mondragon Group, and in 2019 Ikerlan had a revenue of 21 million euros. So here we have an illustrative example that has been provided by Ikerlan based on one of the projects they are developing with one client. And here what we have is one setup in a factory where we have different lines that contain presses that stamp different pieces of hardware. So in line A we have press A1 and press A2, and in line B we have press B1. So let's suppose that each one of these lines are controlled by a device that is called IoT box, that it's our IoT device, that it's able to send monitoring data to other parts of the system. So in this case, this monitoring data, we can see that is sent in JSON to a message broker that will deliver it to interested parties. Here we have an example of the JSON message of the monitoring data that is sent. For example, the timestamp and the value in pascals of the press that is being done by the press itself. So as I said, for example, this information can be sent to the cloud to process them and to detect if there is some kind of malfunctioning of the system. But for example, there could be the case if there's no care from part of the developers in the implementation of the system, that for example could be the case that the name of the topic is introduced in the wrong way. For example, here we see that we are ending the topic name using monitoring instead of monitor, or for example that the message is sent with a different structure than the one expected by the receiver, for in this case the cloud. So in this case this can cause all kind of malfunctioning of the system. We can lose messages, we can lose information, we can have runtime problems, that we can have a crash of the system. So it's really difficult to maintain consistency in this kind of architectures. So what is true is that we need one single source of truth in our development process that centers all the information that we know about our infrastructure, about our architecture. So here is where we saw AsyncAPI as this possible specification that could be used to capture all the information we that is interesting to keep about the infrastructure itself. So, for example, this is the specification of the system I have just shown you. There's no need to see the details of the specification, but you can see that it's only some tenths of code in JSON. So we can distinguish different sections in this specification. We have first the definition of the version of AsyncAPI standard we are using, a section about the information of the API, a section about the servers in our infrastructure, a section about the channels or the so-called topics that can be published and subscribed in our infrastructure, and finally some kind of reusable components that can be used in different parts of our definition. So if you look into the details of this specification, for example, the info section contains the title of the API, the version of the API, the license of the API, etc. For example, the servers, as I said, it contains the list of servers that play a role in our infrastructure. For example, the channels, as I said, is the information about the topics. So here we have this monitor topic I just show you, indicating that, for example, it has in the middle an ID, that it's a parameter, that it's encoded in the topic name, and later we have the publish and subscribe operations that have those IDs and also have a given message that is sent when this operation is invoked. This message in this case is a reference to one component that, as I said, they are defined in the components section, in this case in the messages section, and the status message contains a given payload that is also defined in the other section, that it's schemas of the components section. So finally we have this schema for the line info object. This is done using JSON schema. This is a simple definition in JSON schema, and the same for press info. So basically this is all the information that we can capture about the example I have just shown you. But at the moment we defined or we decided to use AsyncAPI, there was a lack of tooling in the community. So what we decided is to use both Eclipse and Xtext to build the tooling that is able to take an AsyncAPI specification and to create all the code that can help us to implement all this infrastructure in an easy way. So this is, as I said, we called our prototype AsyncAPI toolkit, that in the end is this model-based approach for developing event-driven architectures with AsyncAPI. So this is basically our approach. So we start from the AsyncAPI specification, and we manually have defined the AsyncAPI grammar using Xtext. We have paid attention to do kind of natural mapping between the specification and the grammar, so we can obtain an AsyncAPI meta model that is quite understandable. So when a developer wants to use our toolkit, what he or she does is basically to do the specification using JSON, and automatically we obtain an API model that is conformant to our AsyncAPI meta model, and finally we have implemented some model to text transformation to generate an internal DSL that assists developers to create or to implement the client code that does all the logic on top of the infrastructure that is provided by AsyncAPI. So I'm going to explain this a bit in more detail. So basically, from the document that is the AsyncAPI specification, as I said, what we do is to define the Xtext grammar. So we have different rules. In this case, this is the top rule that, as we said, matches with the top level sections, the AsyncAPI section, the info section, the server section, the channel section, and the component section. And each one of these parts of the rule also match with lower rules. For example, this is the rule to define the information of the API. So all these Xtext rules of the grammar basically is like a Backus grammar. This is automatically transformed to a meta model, And this meta model, as I said, has been developed in such a way that is quite high level, so that we have an element for the AsyncAPI specification, we have the elements for the classes for the top level elements, for example, the information, the server, the components, the channels, etc. So if we go inside the channel, we have also operations, parameters, schemas, etc. So this is from the part that is done at the design time. And basically, when the developer wants to generate the code, what he does or she does is to define this AsyncAPI definition. This is the same definition I have just shown a few slides before. So here we have the AsyncAPI with the info, the server, the channels, and the schemas and messages. So from this, we obtain automatically the instance of the AsyncAPI meta model. This is something that later we can use to integrate this definition in other model-driven tasks. And finally, from this model, we can generate all the code. For example, here there's a small screenshot of the project explorer with the code generated for this example. Here we have, for example, that we obtain one package for each one of the topics, in this case the IoT box ID monitor topic. Here we have the schemas with the classes that give support to create the payloads of our meta model, of our specification, and so on. And as I said, what we do is to generate an internal DSL that uses the definition of the client code in our infrastructure. So let's see an example of this. So as I said, basically this is an example message that is going to be sent from, for example, from line A to the message broker and later to the cloud. That is not shown here for simplicity purposes. So as I said, first we have an ID with the ID of the line, and later on we have an array of the presses with the press information, and each one of the parts of the array has an ID, a timestamp and a value, and also an ID and a timestamp and value. So let's start to create this program, the program that creates this message and sends it to or publishes it so that it is consumed by any other element in the infrastructure. So we are going to create a main method in a publish class, and we are going to make use of our DSL, of our internal DSL. So first, what we are going to do is to start creating a new payload that is this whole message. So what we do is to call the line info, because we want to create a line info element. We obtain a builder for line infos. And we said first, we specify that we want a line info with an ID of line A. We see that here we already have one method that refers to the name of the property in the JSON message. So we are creating the messages using the same concepts that we have in our definition of the API. So we are creating the builder, we are setting the ID. Next, we say, okay, we are going to create a set of presses, and we are going to add them to the list of presses of the line info. So we call the method add to presses, and also now we are going to create each one of this press information that is going to be added to the line information. So now that we have the new builder, we set the ID of the press, we set the timestamp of the press when this measure is being done, and finally we set the value of the measurement in this press. So this information is built and is added to the presses, and the same for the next press. So for example, here we call the method add to presses, and again we create a new builder, we set all the information with ID, with timestamp, with value, etc. So now we already have in this payload the message that is going to be sent, and this is something that has been done automatically or semi-automatically using our DSL. And using the DSL also, we are sure that, for example, we are not messing up with the data types. For example, we know that the value is a float value, is a real value. So if we try to put here, for example, a string, this is going to fail. This is not going to compile. Okay, so we are also taking advantage of the typing system of the language to be sure that the definitions and the creation of the messages is consistent with the specification. So now that we have this message created, we finally build it, and next, as we saw, for example, the IoT box slash monitor, it's a topic with a parameter inside. So for example, this part in the middle, that is box 1, it's a parameter. So now here we are creating the list of parameters, and we are saying that the ID of this parameter, or the parameter ID, takes the value box 1. So we also create the list of parameters. And finally, we call the method publish, setting the payload and the params. And we are publishing the status in this program, and finally the message is created in line A and it's sent to the message broker. The message broker in the end will deliver it to the other interested party, for example, as I said, the cloud device. So basically this is all. The point is that basically with the AsyncAPI toolkit we can use AsyncAPI as the single source of truth when designing and running this an event-driven architecture, and we can do it because we have a tooling support that indeed provides us with all the tooling, code, libraries and infrastructure that allows us to do it. And basically AsyncAPI toolkit is using model-based techniques for first, lowering the development and deployment time. Second, to obtain better code quality, because most of the code, at least for the DSL part, for the internal DSL, the creation of the messages and the sending and receiving messages is automatically generated. Also, we are increasing the maintainability, because if the specification changes and we regenerate the libraries, in the end we will be notified when our client code is no longer compliant with specification. We have a better requirements management, because in the end the requirements of our infrastructure are directly encoded in the AsyncAPI specification, and also we have better documentation, because in the end the AsyncAPI specification is also used to generate documentation. So this is one statement that was said by people from Makerland. So basically they see that the AsyncAPI toolkit supports most of the phases of their development cycle, from requirements to code generation. So this is something that is going to be used in next projects there in Makerland to develop IoT applications to new clients. So this is basically all about this presentation. Here you have the prototype if you want to test it. Thank you very much for listening, and I'm welcome to your questions. Thank you.